What will we see when the sun dies? Look up at the sky on a clear day. That brilliant point of light that makes life possible, that warms your skin, that you've seen every single day of your existence. It's dying. Not today, not tomorrow, but it is dying. And when it does, the transformation will be so spectacular, so utterly transformative, that it defies imagination. So, what will we see when the sun dies? It's a question that seems almost too vast to contemplate. The sun feels eternal, doesn't it? It's been there every morning of every day for as long as humans have existed. For as long as life itself has existed on Earth. 4.5 billion years of steady, reliable light. But eternity is an illusion. The sun, like everything else in the universe, has an expiration date. Let's start with what we're actually dealing with here. The sun is classified as a yellow dwarf star, though if you're being technical, it's more of an orange-white color, but yellow dwarf is the term astronomers use. And despite the word dwarf in its name, it's actually bigger than about 80% of all stars in our galaxy. It's just that the truly massive stars out there make it look small by comparison. In terms of cosmic lifespans, our sun has a total life expectancy of about 10 billion years from birth to final death. 10 billion years. Let me put that in perspective for you. If the sun's entire lifetime were compressed into a single human lifespan of 80 years, all of recorded human history, every pharaoh, every empire, every war, every work of art, would fit into the last 7 seconds. We are living in the middle chapters of a story that began long before Earth even existed and will continue long after everything we know has turned to dust. And here's something that might surprise you. The sun is roughly halfway through its life right now. At 4.6 billion years old, we're at the midpoint. If the sun were a person, it would be middle-aged, settled into its career, running on a steady routine. It's been fusing hydrogen into helium in its core for all those billions of years, and it's got billions more to go before the fuel runs out. We are living in the sun's stable, productive years. The crisis is still ahead. Now, you might be thinking this is a story about something rare, something unique to our particular star. But it's not. The death we're going to witness, or rather, that our distant descendants might witness if humanity survives that long, is actually the most common stellar death in the galaxy. About 90% of all stars in the Milky Way will die in a similar way to our sun. These are the low to medium mass stars, the ones that don't have enough gravity to go out in a blaze of glory. The universe is filled with stars like ours, all marching toward the same fate. And that fate is not what you might expect. When most people imagine a star dying, they picture something catastrophic. An explosion. A supernova. A spectacular detonation that tears the star apart and sends shockwaves across light years of space. And yes, that does happen, but not to stars like the sun. The sun's death will not be an explosion or a supernova. It simply doesn't have what it takes. Supernovae are reserved for the truly massive stars, the ones with at least 8 times the sun's mass. Those giants live fast and die hard, burning through their fuel in just a few million years before exploding in one of the most energetic events in the universe. But our sun? Our sun is going to die a slower, stranger, and in many ways more beautiful death. It will also not end as a black hole. Black holes require even more mass than supernovae do. You need a star at least 20 to 25 times the mass of the sun to create a black hole after it dies. The sun has insufficient mass for that ultimate gravitational collapse. It won't compress down into a point of infinite density where space and time break down. Instead, it will end its days as something called a white dwarf, a stellar ember, a cosmic remnant, the cooling core of what once was a star. But getting to that endpoint is where the real story lies. Because this entire process, from the first signs of aging to the final fade into darkness, will unfold over the next 5 billion years. 5 billion years of transformation. 5 billion years of changes so gradual that if you could watch it in real time, you'd die of old age billions of times over before you noticed anything different. And yet, when those changes do come, they will reshape our entire solar system. The sun will swell. It will change color. It will pulse and throb. It will shed its outer layers into space, creating shells of glowing gas that will expand outward for thousands of years. And at the center of it all, the tiny, dense core that remains will shine with a fierce, white-hot light, not from fusion anymore, but simply from the residual heat of billions of years of stellar fire, slowly radiating away into the cosmic void. This is not a quick death. This is not a sudden ending. This is a transformation that will happen so slowly that entire species could rise and fall on Earth during the process, if Earth even survives it. And that's the key question we'll be exploring. What exactly will we see? What will the sky look like? What will happen to our planet? What are the stages of this cosmic transformation? Over the next several hours, we're going to walk through this process step by step. We're going to witness the death of our star in exquisite detail. And by the end, you'll understand not just what will happen to the sun, but what it means for everything that orbits it, including us. The clock is ticking. Not quickly, but inevitably. The sun is dying. And the show, when it finally begins, will be unlike anything the universe has to offer. The first warning signs. If you're imagining the sun's death as something sudden, something dramatic that arrives without warning, think again. The sun doesn't just wake up one day and decide to die. It gives us warning signs. Plenty of them. The problem is, those warnings span timescales so vast that they make human civilization look like a brief flicker. The process begins not with fire and fury, but with something far more subtle: brightness. The sun's luminosity increases by about 10% every billion years. 10% doesn't sound like much, does it? You might think, well, that's barely noticeable. We get more variation than that between winter and summer due to Earth's elliptical orbit. But here's the thing about a 10% increase in solar luminosity. It's not just about things getting a little brighter. It's about energy, heat, radiation. And when you're talking about the amount of energy the sun pumps out, a 10% increase is absolutely catastrophic for a planet at Earth's distance. This increase happens because of what's going on in the sun's core. As hydrogen fuses into helium, that helium builds up in the center. Helium is denser than hydrogen, so the core gradually becomes more compressed, more compact. And when you compress something, it heats up. The temperature rises. The fusion reactions speed up. The sun doesn't burn brighter because it's running out of fuel. It burns brighter because it's actually getting more efficient at fusion. It's like a fire that burns hotter as the coals get denser. So, what does this mean for Earth? In 1 to 2 billion years, Earth's oceans begin to boil. Not a rolling boil like a pot on a stove. This is a gradual, relentless process. The increased solar radiation heats the surface. Water evaporates into the atmosphere. And here's where things get nasty. Water vapor is a greenhouse gas. It's actually a more potent greenhouse gas than carbon dioxide. As more water enters the atmosphere, it traps more heat. That trapped heat causes more water to evaporate. More water vapor means more heat trapped. More heat means more evaporation. You see where this is going. This is called a runaway greenhouse effect, and it's the same thing that happened to Venus billions of years ago. The atmosphere becomes thick with steam. Temperatures soar. The oceans don't just get warmer, they literally cook away, molecule by molecule, evaporating into space. Eventually, there's no liquid water left on the surface at all. Earth becomes a scorched, steaming hellscape, where the surface temperature exceeds the boiling point of water. The clouds aren't white and fluffy anymore. They're dense, choking, superheated vapor. And as this happens, something else shifts. The habitable zone moves outward past Earth. Every star has a habitable zone, sometimes called the Goldilocks zone. That sweet spot where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. As the sun's luminosity increases, that zone moves farther out. In 1 billion years, Earth will be on the inner edge of the habitable zone, getting roasted. In 2 billion years, Earth will be well inside the zone where no planet could maintain liquid water. The habitable zone will have moved outward, perhaps to somewhere between Mars and the asteroid belt. But here's the truly sobering part. Complex life on Earth ends long before the red giant phase. Long before the sun swells up and engulfs the inner planets. Long before the really dramatic stuff happens, Earth will already be a dead world. We're not talking about 5 billion years from now. We're talking about a billion, maybe 1.5 billion years at most. Current estimates suggest that Earth becomes uninhabitable around 1.4 billion years from now. That's when the combination of increased solar output, atmospheric loss, and runaway greenhouse effects make it impossible for life, as we know it, to survive. The microbes might hang on a bit longer, the extremophiles that can survive in the harshest conditions. But the forests, the animals, the ecosystems, the complex web of life that makes Earth so unique, all of that ends. 1.5 billion years. It sounds like forever. It sounds like we have all the time in the world. But remember, Earth has already been around for 4.6 billion years. Life has been around for about 3.8 billion years. Complex life, multicellular organisms have only been around for about 600 million years. We're talking about roughly doubling the age of complex life before it all ends. In cosmic terms, that's not a long time at all. And the sun doesn't just sit there passively getting brighter. As it ages, other things change too. Solar winds begin intensifying, stripping planetary atmospheres. The solar wind is a stream of charged particles that the sun constantly spews out into space: protons, electrons, alpha particles, all flying outward at hundreds of kilometers per second. Right now, Earth's magnetic field protects us from most of it, channeling those particles toward the poles where they create the auroras, those beautiful green and red curtains of light in the Arctic and Antarctic skies. But as the sun ages and its luminosity increases, those winds get stronger, more intense, more violent. And they don't just create pretty lights, they slam into planetary atmospheres and tear them apart, molecule by molecule, atom by atom. Planets without strong magnetic fields are especially vulnerable. Venus, our sister planet, already lost most of its water billions of years ago. But in this new era of intensified solar winds, something even stranger happens. Venus develops a comet-like tail. The solar wind is so strong that it strips away the upper atmosphere faster than it can be replenished. Atoms and molecules are ripped from the planet and blown downwind in the solar breeze, creating a long, thin tail of atmospheric gases streaming away from the sun. Venus essentially becomes a giant comet, leaving a trail of its own atmosphere across millions of kilometers of space. And then there's Mars. Poor Mars, which already lost most of its atmosphere billions of years ago when its magnetic field shut down. Mars today still has a thin whisper of an atmosphere, mostly carbon dioxide, about 1% the density of Earth's. But with the solar winds intensifying, even that thin atmosphere doesn't stand a chance. Mars becomes an exposed, airless rock, completely stripped down to its bare surface. Any molecules still clinging to that cold, red world are blown away into space. Mars becomes even more dead than it already is, if that's possible. Earth fares better than Mars because of our magnetic field, but only for a while. The magnetic field can deflect charged particles, but it can't stop the relentless increase in heat. And as the oceans boil away, as the water vapor escapes into space, Earth's atmosphere changes composition. It thins. The protective blanket that kept us safe for billions of years begins to unravel. Eventually, even Earth will feel the full force of those solar winds, and they will strip away what's left. By this point, if humans are still around, and that's a very big if, survival would require leaving Earth entirely. There's no adapting to this. No bunker you can build deep enough. No technology that can shield you from a sun that's cooking the entire planet. If humanity wants to survive, we need to become a spacefaring species. We need to leave our home world and find somewhere else in the solar system, or beyond, where we can establish a new home. Maybe we head to the moons of Jupiter or Saturn, which might actually become habitable as the sun's luminosity increases and the habitable zone shifts outward. Maybe we build space stations, artificial worlds where we create our own environment independent of any planet. Maybe we develop the technology to travel to other star systems entirely, to find a younger, more stable sun around which to build a new civilization. Or maybe we don't make it that far. Maybe something else ends human civilization long before the sun becomes a threat. War, disease, asteroid impact, our own self-destruction. 1 billion years is an incomprehensibly long time. Homo sapiens have only existed for about 300,000 years. All of recorded history is less than 6,000 years old. Imagining what humans might be in 1 billion years, or whether we'll exist at all, is essentially impossible. But one thing is certain. If any descendants of humanity do survive to see these first warning signs of the sun's death, they will be living through the end of Earth as a living world. They'll watch the oceans vanish. They'll see the skies turn from blue to a hazy, thick white, then to a sickly orange as the atmosphere changes. They'll witness the last of the forests die, the last of the animals go extinct, the last pockets of life struggle and fail in increasingly extreme conditions. And through it all, the sun will just keep getting brighter, hotter, more intense, completely indifferent to the life it's extinguishing on the planet that has orbited it for billions of years. This is just the beginning. The warning signs. The slow burn. The sun isn't even starting to die yet. Not really. It's still in its main sequence phase, still fusing hydrogen into helium in its core like it has for billions of years. But the clock is ticking down, and the changes are starting to compound. The question isn't whether Earth will become uninhabitable. The question is whether anyone will be around to witness it, and if so, whether they'll have anywhere else to go. Hydrogen runs out. 5 billion years from now, something happens that hasn't happened since the sun was born. The core runs dry. The sun exhausts its hydrogen fuel in about 5 billion years. Not all of its hydrogen, mind you. The sun is still mostly hydrogen even at this point. But the hydrogen in the core, where the temperature and pressure are high enough for fusion to occur, that hydrogen is gone. Used up. Converted into helium through billions of years of nuclear fusion. Every second for 5 billion years, the sun has been fusing about 600 million tons of hydrogen into helium. That adds up. And eventually, inevitably, the tank hits empty. This is a pivotal moment in the life of any star. It's the end of an era. For the sun's entire adult life, its main sequence phase, as astronomers call it, it has existed in a state of perfect balance. Gravity pulls inward, trying to crush the star down into a single point. The pressure from fusion pushes outward, resisting that collapse. These two forces have been locked in equilibrium for billions of years, maintaining the sun's size, its temperature, its steady output of energy. It's been stable, predictable, reliable. But when the hydrogen in the core runs out, that balance breaks. Hydrogen fusion in the core stops. Just like that. The core has been fusing hydrogen at a rate of millions of tons per second, generating an enormous amount of energy, creating the outward pressure that holds the sun up against its own gravity. And then it just stops. The reactions cease. The energy production drops to zero. In the core, at least. Now, you might think this is the beginning of the end, that the sun would start to cool down and fade. But the opposite happens. This is where things get strange. With no outward pressure from fusion to resist it, gravity takes over. The core contracts under gravity. Without the heat and pressure from ongoing fusion reactions, there's nothing to hold it up anymore. The helium-rich core, dense and heavy, begins to collapse inward. It shrinks, compresses. And as it does, it heats up because when you compress a gas, or in this case a plasma, it gets hotter. This is basic physics, the same reason a bicycle pump gets warm when you compress air into a tire. The core gets smaller and smaller, hotter and hotter. But here's the crucial thing. It's not hot enough yet to fuse helium. Helium fusion requires much higher temperatures than hydrogen fusion, about 100 million degrees Celsius compared to the 15 million degrees needed for hydrogen. So the core just sits there, contracting, heating, but not fusing. It becomes what's called an inert helium core. Dead. Compressed. Waiting. But the sun isn't done yet. Not by a long shot. While the core is contracting, something else is happening in the layers just above it. Remember, the sun still has plenty of hydrogen, it's just not in the core anymore. That hydrogen is in the shells surrounding the core. And as the core contracts and heats up, it starts heating up those surrounding layers. Eventually, they get hot enough for fusion to begin. Hydrogen fusion continues in a shell around the core. This is called shell burning, and it's a very different beast from core burning. The shell is thinner, more compact, and because it's closer to the intensely hot contracting core, the temperatures are actually higher than they were in the original core. The fusion reactions in this shell are faster, more energetic, more intense than the steady fusion the sun maintained for billions of years. And this is where something really counterintuitive happens. Something that seems to violate common sense. When the core stopped fusing and started contracting, you'd expect the sun to get smaller overall, right? The core is collapsing inward, so the star should shrink. But it doesn't. Instead, the outer layers of the sun do the exact opposite. They expand. Massively. This is due to something called the mirror principle, and it forces the sun's outer layers to expand. Here's how it works. When the core contracts, it releases gravitational energy. That energy heats up the surrounding layers. And when you heat up a gas, it expands. At the same time, the shell burning around the core is producing more energy than the core ever did. All that extra energy has to go somewhere, and it flows outward, pushing against the outer layers of the sun, causing them to swell. It's like squeezing a balloon in the middle. The center gets smaller, but the ends bulge outward. The core shrinks, and the envelope expands. They move in opposite directions, like a mirror image. Core contracts, envelope expands. The tighter the core squeezes, the more the outer layers bloat. And so the sun becomes a subgiant. It's no longer a main sequence star, but it's not quite a red giant yet either. It's in transition. The sun is getting bigger, but not catastrophically so, not yet. Over the course of a few 100 million years, the sun's radius might increase by 10 or 20%. Not enough to swallow planets, but enough that if you could see it from Earth, if Earth still existed as anything more than a scorched cinder, you'd notice the difference. The sun would look noticeably larger in the sky. And here's something else that happens, something that seems paradoxical. The surface temperature begins dropping. How can the sun be producing more energy, but getting cooler? Because it's getting bigger. The same amount of energy, actually more energy, is now spread out over a much larger surface area. It's the same reason a small fire is hotter than a large fire that produces the same total heat. The energy is more diluted. As the sun expands, its surface moves farther from the core, where all the energy is being generated. The photons, the particles of light, take longer to work their way from the interior to the surface. And when they finally reach the surface and radiate away into space, that surface is cooler than it used to be. The sun's surface temperature, which right now is about 5,500 degrees Celsius, starts to drop, maybe down to 5,000 degrees. Then 4,500. The sun's color begins to change. Right now, the sun is white with a slight yellow tint. As it cools, it gets more yellow, then orange. Eventually, it will have a distinctly reddish hue. This is still a long way off, but the process has begun. The sun is transitioning from a yellow dwarf to what it will eventually become, a red giant. But even though the surface is getting cooler, the luminosity rises dramatically due to increased surface area. Luminosity is the total amount of energy a star puts out. And while each square meter of the sun's surface might be radiating less energy, there are far more square meters now. The sun is like a light bulb that gets dimmer per unit area but gets so much bigger that the total light output actually increases. During the subgiant phase, the sun's luminosity might double or even triple compared to what it is now. And remember, it's already been getting brighter for billions of years due to the gradual increase we talked about earlier. Now that increase accelerates. The sun isn't just getting a little brighter anymore, it's getting a lot brighter. Fast. This is terrible news for any planets still in the inner solar system. Even though the sun's surface is cooler, the total amount of energy hitting those planets is much, much greater. Mercury is being absolutely roasted, its surface melting into a molten sea of metal and rock. Venus is long past the point of having any atmosphere left. It's been stripped bare, baked, transformed into something unrecognizable. And Earth, if it somehow still exists and hasn't been consumed by the earlier stages of the sun's aging process, is now receiving perhaps 2 or 3 times the energy it gets today. There's no coming back from this. No recovery. The sun has crossed a threshold. It's no longer the stable, predictable star that made life possible on Earth for billions of years. It's becoming something else. Something bigger, brighter, and far more dangerous to anything in its vicinity. And this is just the subgiant phase. The Sun is going to get much, much bigger than this. The hydrogen shell burning continues, feeding more and more energy into the Sun's outer layers. The core continues to contract, getting denser, hotter, building up more and more helium ash from the shell burning above it. The pressure at the center increases. The temperature climbs. Slowly, inexorably, the Sun is building toward the next major transition. Because remember, that helium core is still inert. It's not fusing yet. It's just sitting there, getting squeezed tighter and tighter by gravity, getting hotter and hotter from the compression and from the shell burning above it. And there's a limit to how much compression that core can take before something has to give. When the temperature in the core finally reaches 100 million degrees Celsius, helium fusion will ignite. And when it does, the Sun will enter its next phase, the red giant branch. The real transformation will begin. But even now, even in this transitional subgiant phase, the Sun is already a different star than it was. It's bigger, brighter, cooler on the surface, but more energetic overall. The steady, stable yellow dwarf that shone down on Earth for billions of years is gone. In its place is something swollen, unstable, and evolving rapidly on astronomical timescales. The Sun is running out of time on the clock, and the changes are accelerating. The question isn't whether it will become a red giant. The question is what happens when it does, and whether anything in the inner solar system survives what comes next. The red giant rises. And then it happens. The transformation that has been building for hundreds of millions of years finally arrives in full force. The Sun enters its first red giant phase. This is it. This is the moment that defines the end stages of a star like ours. The moment when stability gives way to chaos, when the predictable gives way to the spectacular. The Sun has been a subgiant for several 100 million years, gradually expanding, slowly brightening. But now the helium core has contracted to the point where it reaches critical density and temperature. The shell burning around it intensifies to extraordinary levels. And the outer envelope of the Sun, no longer held in check by any semblance of equilibrium, begins to expand at an accelerating rate. It expands to over 100 times its current size. Let that sink in for a moment. The Sun right now has a radius of about 700,000 kilometers. 100 times that is 70 million kilometers. To put that in perspective, the distance from the Sun to Earth right now is about 150 million kilometers. The Sun is going to expand to nearly half the distance to Earth. Actually, at its maximum extent, it's even worse than that. At maximum, it reaches about 215 solar radii, nearly $1 Australian. 1 astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometers. The Sun is going to swell until it's almost as big as Earth's entire orbit. Picture that. A star so enormous that if you placed it where the Sun is now, its surface would extend almost to where Earth orbits. The Sun will fill half the sky from Earth's perspective, if Earth is even still around to have a perspective. And that's the question everyone wants to know. What happens to the planets? Mercury is engulfed. There's no question about it. Mercury orbits at an average distance of about 58 million kilometers from the Sun. When the Sun expands to 150 million kilometers in radius, Mercury doesn't stand a chance. It's swallowed whole. The tiny, cratered world that has been baking in the Sun's heat for 4.5 billion years finally meets its end, not in a collision or a catastrophic impact, but by being consumed by the very star it's been orbiting. What happens when a planet gets engulfed by a red giant? It doesn't just vanish. The planet enters the Sun's outer atmosphere, which at this point is incredibly diffuse, thinner than any vacuum we can create on Earth. But Mercury is moving at 48 kilometers per second, and even a thin atmosphere creates friction at that speed. Drag. Resistance. Mercury starts to slow down. As it slows, its orbit decays. It spirals inward, deeper and deeper into the Sun's envelope. The temperature rises. Mercury's surface melts, then vaporizes. The metals and rocks that make up the planet turn into gas and mix with the sun's outer layers. The planet essentially evaporates, leaving perhaps a dense core that continues to spiral inward until it too is torn apart by tidal forces and absorbed into the star. Mercury doesn't so much die as it dissolves, atom by atom, into the sun itself. Venus is almost certainly destroyed. Venus orbits at about 108 million kilometers. The sun's maximum radius of 150 million kilometers means Venus is right on the edge. Some models suggest Venus gets engulfed. Others suggest it might just barely avoid direct contact with the sun's surface. But honestly, it doesn't matter. Whether or not Venus technically makes physical contact with the sun's photosphere, it's destroyed either way. If it does get engulfed, it suffers the same fate as Mercury, spiraling inward, vaporizing, torn apart. If it somehow stays just outside the sun's surface, it's still subjected to temperatures of thousands of degrees, intense radiation, and tidal forces that would tear any planet apart. Venus, the planet that has survived billions of years as a hellish greenhouse world, finally meets an end even more violent than anything it's experienced before. And then there's Earth. Earth may narrowly escape engulfment, or not. This is one of the great uncertainties in astrophysics. Earth orbits at 150 million kilometers, and the sun expands to nearly that same distance. So does Earth get swallowed or not? The answer is, we don't know for sure. It depends on a lot of factors that are incredibly difficult to model with precision. First, as the sun expands and loses mass through stellar winds, and in the red giant phase, the sun is losing mass at a prodigious rate. The gravitational pull on the planets weakens. When an object loses mass, its gravitational grip loosens. The planets, including Earth, will slowly drift outward into wider orbits. Earth might migrate from 150 million kilometers out to 160 or 170 million kilometers. That extra distance might be just enough to keep it outside the sun's expanding envelope. But there's a counteracting force: tidal interactions and atmospheric drag. Even if Earth doesn't get fully engulfed, it will be skimming the outermost layers of the sun's atmosphere. And that creates drag, friction, which causes Earth's orbit to decay. Earth could spiral inward even as it's trying to drift outward. The question is which effect wins. Do we drift out fast enough, or do we spiral in too quickly? The most recent models suggest it's going to be close. Some simulations show Earth just barely escaping, ending up in a wider orbit, scorched and dead but intact. Others show Earth spiraling inward and getting consumed. It could go either way. It might come down to factors we can't predict with certainty: variations in the sun's mass loss rate, the exact timing of the expansion, gravitational perturbations from other planets. But here's the brutal truth. Even if Earth survives, even if it avoids being physically engulfed by the sun, it doesn't matter. Because Earth's surface exceeds 2,400 Kelvin. That's over 2,100 degrees Celsius. Hot enough to melt rock. Hot enough to turn granite into lava. The entire surface of the planet becomes a molten ocean of liquefied crust, glowing red-hot like a coal in a fire. Everything on the surface is incinerated. Every mountain, every valley, every trace of tectonic activity, every fossil, every remnant of the life that once flourished here, all of it melts into an undifferentiated sea of molten silicates. If there were any structures left by a long-extinct human civilization, any monuments, any artifacts, any sign that intelligent life once called this place home, they're gone now. Vaporized or melted beyond recognition.
And it gets worse.
Oceans and atmosphere vaporize. Long before the surface melts, the water and air are stripped away. The oceans don't just boil, they flash into steam and then dissociate into hydrogen and oxygen, which are then blasted into space by the intense solar wind and radiation pressure. The atmosphere, whatever might be left of it after billions of years of solar wind erosion, is blown away completely. Earth becomes a bare, molten sphere orbiting a bloated red giant, with no water, no air, no protection of any kind. From a distance, If you could somehow observe this from a safe vantage point, perhaps from the outer solar system, what would you see? You'd see the sun, but not the sun as we know it. The sun appears red-orange due to cooler temperatures around 3,000 Kelvin. Compare that to the 5,500 Kelvin of the sun today. The surface is nearly half as hot. And remember, temperature determines color. Hotter objects glow blue-white. Cooler objects glow red. A red giant surface is cool enough that it gives off most of its light in the red and orange parts of the spectrum. But don't let that cool description fool you. 3,000 Kelvin is still hot enough to vaporize lead, to melt tungsten. It's just cool compared to the sun we know. From Earth's perspective, if Earth still exists, the sun would dominate the sky. Not the small, bright disk we're used to, but an enormous red-orange dome covering a huge portion of the heavens. The sky itself would glow red. There would be no night because the sun is so large it would take up nearly half the visible sky. The horizon itself would be the edge of the sun. And despite being cooler per unit area, its brightness reaches 1,000 to 2,700 times its current level. This is because of the sheer size. Remember the calculation. Luminosity depends on both temperature and surface area. The surface is cooler, which decreases luminosity. But the surface area has increased by a factor of tens of thousands. That increase in area more than compensates for the decrease in temperature. The sun is now pumping out more than 1,000 times more energy than it does today. From Earth's position, if Earth survives, the energy flux, the amount of solar energy hitting each square meter of the planet, would be absolutely catastrophic. We're talking about tens or hundreds of times more energy than Earth receives today. It's like taking Earth and moving it to where Mercury orbits now, except the sun is also producing vastly more energy. There's no surviving this. No shielding yourself from it. No adapting to it. Now, there's something interesting about the color that's worth addressing. When we say red giant, we're using the term astronomers have given these stars, but the visual reality is a bit more nuanced. Red giants appear orange-yellow rather than truly red. The name is somewhat misleading. Yes, they're cooler than main sequence stars, and yes, they emit more of their light in the red part of the spectrum. But to the human eye, most red giants would actually look more orange or even yellow-orange, depending on their exact temperature. A star at 3,000 Kelvin does emit predominantly in the red, but it also produces plenty of orange and yellow light. The human eye integrates all of those wavelengths together, and what you perceive is an orange or amber color, not a pure red. Only the very coolest red giants, the ones below 3,000 Kelvin, start to look genuinely red. Our sun, at around 3,000 Kelvin in its red giant phase, would appear as a deep orange, perhaps with hints of red and yellow mixed in. Still dramatically different from the white-yellow sun we know today, but not the pure crimson sphere you might imagine from the name. If you were somehow standing on the surface of a planet in the habitable zone at this time, maybe one of the moons of Jupiter or Saturn, which might have migrated into more temperate regions as the sun expanded, and you look toward the inner solar system, you wouldn't see planets. You'd see the sun, enormous and orange, with perhaps some slight distortions or anomalies in its outer layers where the planets used to be.
Mercury gone.
Venus gone. Earth, either consumed or reduced to a lifeless, molten rock. And that brings us to the most visceral aspect of this transformation. The sun now dominates the sky of surviving planets. If you're on one of Jupiter's moons, Europa, Ganymede, Callisto, the sun is no longer that distant point of light. It's a vast, glowing presence that takes up a significant portion of the sky. From Jupiter's orbit, about 780 million kilometers from the sun, a red giant sun with a radius of 150 million kilometers would subtend an angle of about 22 degrees across. For comparison, the sun as seen from Earth today is about half a degree across. This red giant sun would appear 44 times larger in the sky. 22 degrees is enormous. Hold your fist out at arm's length. That's about 10 degrees across. The sun would be more than twice the width of your fist. It would be impossible to ignore, impossible to block out. Day and night would lose their meaning because even when the sun is technically on the other side of the planet, its light scatters through the atmosphere, creating a perpetual orange twilight. True darkness would only come in the deepest shadows, in caves, underground. The light would be strange, too. Orange-tinted, casting everything in warm, amber hues. Plants, if any existed on these moons, would have to adapt to photosynthesizing under this different spectrum of light. The psychology of living under an orange sun would be profound. The color of the light affects mood, circadian rhythms, the perception of the world. Humans evolved under a white-yellow sun. Living under an orange giant would feel alien, unsettling, even if you were born into it. And the heat. Even at Jupiter's distance, the energy from a sun producing 1,000 times its current luminosity would be intense. Jupiter receives about 50 watts per square meter from the sun today. With a 1,000-fold increase in luminosity, that becomes 50,000 watts per square meter. That's enough to melt ice, to heat atmospheres, to potentially make some of these icy moons habitable, or at least less frozen. Europa's ice shell might melt entirely, creating a water world with a deep global ocean exposed to space. Ganymede and Callisto could follow suit. The outer solar system transforms from a realm of frozen moons and icy rings into something warmer, wetter, more dynamic. But this is a temporary blessing. The red giant phase doesn't last. The sun is burning through its hydrogen shell fuel at a tremendous rate. The helium core continues to contract, continues to heat up, building toward a critical threshold. And when the core temperature finally reaches 100 million Kelvin, when the pressure and density become high enough, something dramatic is going to happen. The helium is going to ignite. Not gradually, not smoothly, but in a sudden, violent explosion called the helium flash. But we're not there yet. For now, the sun is a red giant. Enormous, bright, and destructive. The inner solar system has been transformed beyond recognition. The familiar order of planets, the neat arrangement we've known for billions of years, is shattered. What remains are the outer worlds, Jupiter, Saturn, Uranus, Neptune, and their moons, basking in the strange orange light of a dying star, watching from what was once a safe distance as the star that gave them birth goes through its death throes. The spectacle has only just begun. The helium flash. Deep in the core of the red giant sun, something has been building. A pressure, a tension, an inevitability. For hundreds of millions of years, the helium core has been contracting under its own gravity, getting smaller, denser, hotter. It's been inert, not fusing, not producing energy, just sitting there accumulating more helium ash from the hydrogen shell burning above it. But gravity is relentless. It never stops squeezing. And with each passing million years, the temperature in that core climbs higher. And then, finally, the contracting core reaches 100 million Kelvin. 100 million degrees Celsius. That's hot enough. That's the threshold. At this temperature, helium nuclei, which are really just the nuclei of atoms, stripped of their electrons by the intense heat, start moving fast enough to overcome the electromagnetic repulsion between them. Helium nuclei are positively charged, and positive charges repel each other. Under normal circumstances, they'd never get close enough to touch. But at 100 million Kelvin, they're moving at thousands of kilometers per second, slamming into each other with enough force to overcome that repulsion and fuse together. And when they do, helium ignites explosively in a helium flash. This is not a gradual process. This is not a smooth transition from inert core to burning core. This is an explosion, a runaway thermonuclear detonation in the heart of the sun. In the span of just a few seconds, literally seconds, the core releases as much energy as the entire galaxy produces in that same time. The helium fusion reactions ignite, and they ignite all at once, throughout the entire core, in a cascading chain reaction. Why does it happen so explosively? Because of something called electron degeneracy. The core at this point isn't a normal gas. It's been compressed so much that the electrons, the subatomic particles that normally orbit around atomic nuclei, are squeezed together as tightly as quantum mechanics allows. When matter is in this state, it's called degenerate, and it behaves very strangely. In a normal gas, when you heat it up, it expands. The pressure increases, the gas puffs up, and that expansion cools it back down. It's a natural safety valve. But in degenerate matter, that doesn't happen. You can pump heat into it and it doesn't expand. The pressure comes from quantum effects, not from temperature, so adding heat doesn't increase the pressure. There's no safety valve. So when helium fusion starts, the energy released heats up the surrounding material, which causes more helium to start fusing, which releases more energy, which heats up more material, and so on. It's a runaway reaction. The temperature in the core skyrockets. In a matter of seconds, the core goes from 100 million Kelvin to over 300 million Kelvin. The energy release is staggering. But here's the thing, the helium flash is contained. It happens deep inside the star, buried under thousands of kilometers of stellar material. The energy doesn't burst out through the surface. It doesn't blow the star apart. Instead, it does something surprising. It actually stabilizes the star. The sudden injection of energy from the helium flash heats the core enough that it lifts the degeneracy. The electrons are no longer packed together as tightly. The core transitions from degenerate matter back to a normal gas. And once it's a normal gas again, it can expand. And when it expands, the temperature drops and the fusion reactions slow down to a sustainable rate. The helium flash is violent, but it's brief. It lasts for just a few seconds, maybe a few minutes at most. And then it's over. What's left is a core that's now steadily fusing helium into heavier elements at a controlled, stable rate. So, what exactly is happening in that core? Helium fuses via the triple alpha process. This is one of the most remarkable nuclear reactions in the universe, and it's the reason carbon, and therefore life, exists at all. Here's how it works. Helium nuclei are also called alpha particles. Each one consists of 2 protons and 2 neutrons. When 2 helium nuclei collide at high enough speeds, they can fuse together to form beryllium-8. But beryllium-8 is wildly unstable. It lasts for only about 1/10 of a trillionth of a second before it splits back apart into 2 helium nuclei. It's so unstable that for a long time, scientists thought it was impossible to build heavier elements from helium. But there's a trick. If a 3rd helium nucleus slams into that beryllium-8 during that incredibly brief instant before it falls apart, the 3 helium nuclei can fuse together to form carbon-12. 3 alphas make carbon. That's the triple alpha process. This reaction is astonishingly improbable. You need 3 particles to collide in just the right way at just the right time. And yet it happens, all the time, in the cores of red giant stars. It happens because the density and temperature are so high that even an incredibly unlikely reaction occurs often enough to matter. Trillions upon trillions of these reactions happen every second in the sun's core. And the result? Carbon forms, with small amounts of oxygen. The carbon-12 can capture another helium nucleus to become oxygen-16. Most of the fusion products are carbon, but some oxygen is produced as well. This is where the carbon and oxygen in your body came from, by the way. Every carbon atom in your DNA, every oxygen atom you breathe, was forged in the core of a dying star through the triple alpha process. We are, quite literally, made of stardust that was created in the final stages of a star's life. Now, with helium burning steadily in the core, something remarkable happens to the sun as a whole. The sun briefly stabilizes. After hundreds of millions of years of chaotic expansion and dramatic evolution, the sun finds a new equilibrium. Helium fusion in the core provides outward pressure. Gravity pulls inward. The 2 forces balance again, just like they did during the main sequence phase, and the sun settles into a stable configuration. This new stable phase is called the horizontal branch, and it enters the horizontal branch phase. The name comes from the Hertzsprung-Russell diagram, which is a chart astronomers use to plot stars based on their temperature and luminosity. During this phase, stars occupy a horizontal band on that diagram, hence the name. For our purposes, what matters is that the sun has stopped expanding. It's reached a new equilibrium. It's no longer growing larger and brighter at a runaway pace. In fact, the sun shrinks slightly during this time. Not back to its original main sequence size, nowhere close to that. But compared to its bloated red giant state, it contracts a bit. The outer layers pull inward. The radius decreases. The surface temperature increases slightly because the surface is now closer to the core where the energy is being generated. The sun might go from 3,000 Kelvin back up to 4,000 or 5,000 Kelvin, shifting from a deep orange to a more yellow-orange color. And this stable helium-burning phase lasts about 100 million years. 100 million years might not sound like much compared to the billions of years the sun spent on the main sequence, but it's still a substantial period of time. It's longer than the entire history of complex life on Earth. It's long enough for entire ecosystems to evolve, for continents to shift, for ice ages to come and go, if there were any planets left capable of supporting such things. During this time, the sun is fusing helium in its core and hydrogen in a shell around the core. Two different fusion reactions happening simultaneously in different layers of the star. The helium burning produces carbon and oxygen, which accumulate in the center. The hydrogen shell burning continues to add more helium to the layer surrounding the carbon-oxygen core. It's a nested structure, a carbon-oxygen core, surrounded by a helium-burning shell, surrounded by a hydrogen-burning shell, surrounded by the vast, extended envelope of the star. This is a much more complicated structure than the simple hydrogen-fusing core of the main sequence Sunday. And it's less stable. The balance is more delicate. The sun is juggling multiple fusion processes, multiple layers, multiple sources of energy. But for now, for these 100 million years, it manages to hold it together. From the perspective of any surviving planets or moons, this is a period of relative calm. The sun is no longer growing. The luminosity is still much higher than it was during the main sequence, perhaps several hundred times brighter, but it's not increasing anymore. If you're living on one of Jupiter's moons, the conditions are stable. Harsh but stable. The orange sun hangs in the sky, enormous but unchanging. Generations could come and go without noticing any difference in the sun's appearance or behavior. But this stability is an illusion. It's temporary. Because the helium in the core, just like the hydrogen before it, is finite. The sun is fusing helium into carbon and oxygen at a tremendous rate, and eventually that helium is going to run out. The core will fill with carbon and oxygen, and helium fusion in the core will stop. And when it does, the same thing that happened before will happen again. The core will contract. The temperature will rise. The shells around it will burn even more furiously. And the sun will expand again, entering a second red giant phase that will be even more dramatic than the first. But we're not there yet. For now, the sun has found a second wind. The helium flash has given it a new lease on life, a new source of fuel to burn. The core is stable. The structure is balanced. For 100 million years, the sun will burn helium and hydrogen in a delicate but sustainable configuration. It's the calm before the final storm, the last period of stability before the sun enters the chaotic, violent end stages of its life. The horizontal branch is the sun's last stand, its final attempt to maintain some semblance of order before entropy and gravity tear it apart. Enjoy it while it lasts. Because what comes next is the beginning of the end. The second giant. 100 million years pass. The helium in the core, which ignited so violently and burned so steadily, begins to dwindle. The reaction slow. The energy output decreases. And finally, inevitably, helium fuel is exhausted. The core is now composed of carbon and oxygen, the ashes of helium fusion. And just like helium before it, carbon and oxygen cannot fuse at the temperatures and pressures available in a star like the sun. You'd need temperatures exceeding 600 million Kelvin to fuse carbon, and the sun's core will never get that hot. The sun doesn't have enough mass. The gravitational pressure isn't strong enough. So the carbon-oxygen core just sits there, inert.
Dead.
Another layer of ash. And once again, with no fusion to support it, the core begins to contract. Gravity reasserts itself. The carbon-oxygen core shrinks, compresses, heats up. The temperature rises, but not enough to ignite carbon. Instead, the heat from the contracting core ignites the layers around it. Helium burning reignites in a shell around the carbon-oxygen core. And above that, hydrogen continues to burn in its own shell. The sun now has two active fusion shells, helium and hydrogen, burning simultaneously in concentric layers around an inert core. And with that, the Sun enters the asymptotic giant branch, the AGB phase. This is the final major evolutionary stage for a star like the Sun. The word asymptotic comes from mathematics. It refers to a curve that approaches a line but never quite reaches it. On the Hertzsprung-Russell diagram, stars in this phase approach a vertical line representing maximum luminosity for their mass, climbing higher and higher in brightness. And the Sun expands again, even larger than before, larger than during the first red giant phase, larger than it has ever been. The radius might reach 200, 250, even 300 times its current size. At this scale, the Sun could potentially extend beyond Earth's current orbit. If Earth somehow survived the first red giant phase, it's almost certainly doomed now. The structure of the Sun at this point is incredibly complex and unstable. You have a carbon-oxygen core that's not fusing. Surrounding that is a shell where helium is fusing into carbon and oxygen. Above that is a shell where hydrogen is fusing into helium. And then there's the enormous, bloated envelope extending outward for hundreds of millions of kilometers. Each layer is interacting with the others, affecting temperature, pressure, and fusion rates. It's a delicate, unstable configuration. And it doesn't stay stable for long. Hydrogen and helium burn in alternating shells. Here's what happens. The hydrogen shell burns steadily, converting hydrogen to helium and dumping that helium onto the helium shell below it. The helium shell accumulates more and more material. Eventually, enough helium builds up that the temperature and pressure spike, and the helium shell suddenly ignites in a burst of fusion. This is called a shell flash, similar to the helium flash in the core, but this time it's happening in a shell rather than the center. When the helium shell flashes, it releases an enormous amount of energy in a very short time. This energy surges outward, disrupting the hydrogen shell above it. The hydrogen shell temporarily shuts down because the temperature and density aren't right anymore. The helium shell burns through its accumulated fuel quickly, then dies down. The star contracts slightly, the hydrogen shell reignites, and the cycle starts over. These are called thermal pulses, and they cause repeated expansions and contractions. Every few thousand years, the Sun undergoes one of these pulses. The star swells up, then contracts, then swells again. It's pulsating, breathing like a living thing. Each pulse lasts for a few hundred years. The time between pulses can range from a few thousand to tens of thousands of years, depending on the exact conditions in the star. During these pulses, the Sun loses mass at extreme rates. The outer layers are barely bound to the star anymore. The gravity at the surface is incredibly weak because you're so far from the core. And every time there's a thermal pulse, energy surges through the envelope, heating it up, pushing it outward. Material at the surface reaches escape velocity and just drifts off into space. The stellar winds reach 10 to 100 times current levels. Right now, the Sun loses about 1 million tons of material per second through the solar wind. That sounds like a lot, but it's actually negligible compared to the Sun's total mass. Over the Sun's entire main sequence lifetime, it's lost maybe 0.1% of its mass through solar wind. But in the AGB phase, the mass loss rate increases by orders of magnitude. The Sun might lose 10 million tons per second, 100 million tons per second, maybe more during the most intense pulses. Over the course of the AGB phase, which lasts perhaps a few 100,000 years to a million years, about 30% of the Sun's total mass is lost. Nearly a third of the Sun's material is blown away into space. This is an enormous amount of mass. The Sun currently has a mass of about 2 times 10 to the power of 30 kilograms. Losing 30% means shedding roughly 6 times 10 to the power of 29 kilograms. That's equivalent to the mass of about 200,000 Earths, just blown away into interstellar space as gas and dust. This mass loss has profound effects on the solar system. When the Sun loses mass, its gravitational pull on the planets weakens. And when the gravitational pull weakens, the planet's orbits expand. It's a consequence of orbital mechanics. The farther out a planet is, and the less massive the central star, the wider the orbit. Planetary orbits widen due to mass loss. All of the planets drift outward. It's a slow process, but over hundreds of thousands of years, it adds up. The amount of orbital expansion depends on how much mass the Sun loses and how quickly it loses it, but the effect is significant. Earth's orbit may expand to 1.5 to 2 Australian dollars. Remember, Earth currently orbits at 1 Australian dollar, 150 million kilometers from the Sun. If Earth's orbit expands to 1 Australian dollar and 50 cents, that's 225 million kilometers. If it reaches 2 Australian dollars, that's 300 million kilometers, twice as far from the Sun as it is now. That might sound like it would save Earth from being engulfed by the expanding Sun. And in theory, it could. The orbital expansion happens at the same time as the Sun expands, so it's a race between the Sun's surface moving outward and Earth's orbit moving outward. But there's a problem. Tidal drag may still pull Earth inward. Even as Earth drifts outward due to the Sun's mass loss, it's also experiencing drag from passing through the Sun's extended atmosphere. The Sun's envelope at this point is enormous and incredibly diffuse, but it's not a perfect vacuum. There's still some density there, however slight. And as Earth plows through that tenuous gas at 30 kilometers per second, there's friction.
Drag.
This drag exerts a force opposing Earth's motion, which causes the orbit to decay. Earth slows down, which makes it spiral inward. It's the same effect that eventually causes satellites in low Earth orbit to fall back to Earth. Atmospheric drag gradually robs them of energy, and they spiral inward. Earth is experiencing the same thing, just on a much larger scale and over a much longer time scale. So, which effect wins? Does Earth drift outward fast enough due to mass loss, or does it spiral inward due to tidal drag? The answer is, it depends. It depends on the exact rate of mass loss, the exact density of the Sun's outer envelope, the exact timing of the thermal pulses. Different models give different answers. Some suggest Earth drifts outward and survives. Others suggest the drag is too strong and Earth spirals into the Sun. It's impossible to say for certain. What we do know is that if Earth survives at all, it will be a charred, lifeless cinder in a much wider orbit than it occupies now. And honestly, whether it's engulfed or not is almost a technicality at this point. Earth, as we know it, as a world that once supported life, is long gone. The outer planets, on the other hand, are in a much better position. Outer planets drift farther away. Jupiter, Saturn, Uranus, Neptune, all of them move to wider orbits as the Sun loses mass. Jupiter might drift from 5 Australian dollars out to 6 or 7 Australian dollars. Neptune, currently at 30 Australian dollars, might end up at 35 or 40 Australian dollars. They're far enough from the Sun that tidal drag is negligible. There's no danger of them spiraling inward. They just drift outward and watch the Sun's death throes from an increasingly safe distance. But even the outer solar system isn't immune to chaos. Some moons and Kuiper belt objects destabilize. The Kuiper belt is the region beyond Neptune filled with icy bodies, dwarf planets like Pluto, comets, frozen remnants from the formation of the solar system. As the Sun loses mass and the orbits of the giant planets shift, the gravitational landscape of the outer solar system changes. Orbits that were stable for billions of years might suddenly become unstable. Resonances shift. Perturbations accumulate. Some Kuiper belt objects get flung inward toward the Sun. Others get ejected entirely, thrown out of the solar system into interstellar space. Moons of the outer planets might experience changes in their orbits as well. Tidal forces shift, orbital periods change, and in extreme cases, moons could be lost. The solar system that has existed in more or less its current configuration for 4.6 billion years is being torn apart. Not destroyed in a single catastrophic event, but gradually dismantled as the Sun loses mass, expands, pulses, and sheds material into space. The orderly arrangement of planets, the stable orbits, the predictable dynamics, all of it is breaking down. And through it all, the Sun continues to swell. The surface grows cooler as it expands, perhaps down to 2,500 or 2,000 Kelvin, glowing a deep red now, truly earning the name Red Giant. But the luminosity remains enormous because of the sheer size. The sun is so large that even with a cool surface, it's radiating thousands of times more energy than it did in its youth. If you're observing from the outer solar system, from one of Saturn's moons, perhaps, or a habitat in the asteroid belt that's now been pushed outward, the sun is no longer recognizable. It's a massive, bloated sphere of glowing red gas, pulsing and throbbing with thermal pulses, surrounded by shells and streamers of ejected material. It's shedding its outer layers in great waves, creating a halo of gas expanding outward into space. The wind from the sun is so strong that it pushes dust and gas into intricate patterns, creating shells, arcs, and filaments visible from vast distances. The sun is dying. Not quickly, but messily. It's shedding itself, layer by layer, pulse by pulse, losing mass and luminosity and structure. The end is coming. The final transformation is at hand. And when the last of the thermal pulses fades, when the envelope has been stripped away entirely, what will be left is the core. The tiny, dense, incredibly hot core that has been at the center of all this chaos. The carbon-oxygen ember that represents all that remains of the sun's nuclear furnace. But before we get there, before the sun finally sheds the last of its envelope, there's one more spectacle to witness. One final, breathtaking display that will mark the transition from dying giant to stellar remnant. The planetary nebula is about to be born. The planetary nebula. The thermal pulses become more frequent, more violent, more erratic. The envelope of the sun is barely holding together anymore. Most of the hydrogen has been blown away. What's left is a thin, extended shell of gas, weakly bound to the core by gravity that can barely reach across the hundreds of millions of kilometers separating them. And then, finally, the last connections break. The sun ejects its outer layers into space. This isn't an explosion. It's not a supernova, not a detonation. It's more like the star is exhaling for the last time, breathing out everything that's left of its outer envelope. The stellar winds, already intense, become overwhelming. The radiation pressure from the hot core pushes outward. The thermal pulses send waves of energy rippling through what remains of the atmosphere. And the outer layers, no longer bound by gravity, simply drift away. Over the course of perhaps 10,000 to 50,000 years, the sun sheds the last 20 or 30% of its mass. The material flows outward in all directions, expanding into the space around the star. Shells of gas, filaments of ejected material, clouds of atoms that were once part of the sun itself, all of it moving outward at tremendous speeds. And as this happens, a planetary nebula forms. The name is a historical accident. When these objects were first discovered in the 1700s through early telescopes, they appeared as small, round, disc-like shapes, similar in appearance to planets like Uranus or Neptune. So astronomers called them planetary nebulae. But they have nothing to do with planets. They're the ejected envelopes of dying stars, glowing shells of gas surrounding the exposed cores of what used to be red giants. The nebula expands at under 100,000 miles per hour. That's roughly 10 to 40 kilometers per second, depending on the exact dynamics of the ejection. It sounds fast, and it is by human standards. But on astronomical scales, it's relatively slow. The gas is moving outward, expanding, thinning out as it goes. Over thousands of years, the nebula grows from a small cloud surrounding the sun to an enormous structure light years across. But it's not very dense. Gas densities range from 100 to 10,000 particles per cubic centimeter. To put that in perspective, the air you're breathing right now contains about 2.5 times 10 to the power of 19 molecules per cubic centimeter. That's 25 billion trillion particles. The planetary nebula is a near-perfect vacuum by any terrestrial standard. But in space, where the average density of the interstellar medium is about 1 particle per cubic centimeter, a density of 100 or 10,000 particles per cubic centimeter is actually quite substantial. It's a cloud, a diffuse one, but a real concentration of matter. And this gas doesn't just drift silently through space. It glows brilliantly. At the center of the expanding shell, the core of the sun is now exposed. All the overlying layers have been stripped away. What's left is a tiny, incredibly hot object, a white dwarf in the making, though it's still too hot to officially be called that yet. The surface temperature of this exposed core is around 100,000 Kelvin or higher. Compare that to the 5,500 Kelvin of the Sun's surface today. This is 20 times hotter. Hot enough to emit enormous amounts of ultraviolet radiation. And that ultraviolet radiation from the core ionizes the gas. Ionization is the process of stripping electrons away from atoms. When a high-energy ultraviolet photon hits an atom of hydrogen or helium or oxygen, it can knock an electron completely off the atom. The atom becomes ionized, positively charged. And when that electron eventually recombines with an ion, it releases energy in the form of visible light. Different elements emit different colors of light when they recombine. Hydrogen glows red. Oxygen glows green and blue-green. Nitrogen glows red and orange. Sulfur contributes to reds as well. The exact color of the nebula depends on which elements are present and in what quantities. Most planetary nebulae glow predominantly green because of doubly ionized oxygen atoms that have lost 2 electrons. But they also have reds, blues, and other colors mixed in, creating a complex, multi-hued structure. The result is one of the most beautiful phenomena in astronomy. The nebula glows for 10,000 to 50,000 years. For tens of thousands of years, the expanding shell of gas shines with its own light, illuminated from within by the ultraviolet radiation of the dying star at its center. It's visible from across the galaxy. From thousands of light years away, you could see it, a faint, glowing cloud, a testament to a star's death. And what's in that cloud? What is the nebula made of? It's not just hydrogen and helium, though those are the most abundant elements. This is the material that was processed in the Sun's interior through billions of years of fusion. Carbon, oxygen, helium, and heavier elements enrich space. Carbon and oxygen, forged in the helium-burning phases. Nitrogen, created through a complex chain of reactions involving carbon and hydrogen. Traces of neon, magnesium, silicon, sulfur. All the elements up to iron that can be created through fusion processes in a star of the Sun's mass. And beyond that, even heavier elements created through a process called the S process, the slow neutron capture process, which happens in the shells of AGB stars when free neutrons are captured by atomic nuclei, gradually building up heavier and heavier elements. The Sun is returning to the cosmos all the material it borrowed 4.6 billion years ago when it formed from a collapsing cloud of gas and dust. But it's giving it back in a more processed form. The hydrogen and helium that went into making the Sun have been partially converted into heavier elements. And now those elements are being dispersed into space, where they'll mix with the interstellar medium, become part of new clouds, and eventually be incorporated into the next generation of stars and planets. This is how the universe becomes chemically enriched over time. The first stars were made of almost pure hydrogen and helium, the only elements created in the Big Bang. But when those stars died, they produced heavier elements and ejected them into space. The next generation of stars formed from gas that contained those heavier elements. They lived, died, and added even more heavy elements to the mix. Generation after generation, the universe becomes richer in carbon, oxygen, nitrogen, iron, and all the other elements that make up planets and life. You're made of atoms that were inside stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stellar interiors and dispersed into space when those stars died. Some of it came from supernovae, the explosive deaths of massive stars. But a lot of it, the carbon, the nitrogen, the oxygen, came from planetary nebulae like the one the Sun will create. You are, quite literally, the material remnants of long-dead stars. Now, for a long time, there was some debate about whether a star like the Sun would actually produce a visible planetary nebula. Some older models suggested that stars on the lower end of the mass range, stars just slightly more massive than the Sun, or like the Sun itself, might not shed enough material in the right way to create a bright, visible nebula. Maybe they'd just fizzle out, losing their envelopes gradually without the dramatic ejection that creates the glowing shells. But new models confirm sun-like stars do form visible nebulae. More detailed simulations, better understanding of mass loss rates, improved observations of planetary nebulae in other galaxies. All of this has confirmed that yes, the sun will produce a planetary nebula. It might not be the largest or the brightest one out there, but it will be real and visible. For tens of thousands of years after the sun dies, there will be a glowing cloud marking the spot where our star used to be. What will it look like? That's hard to say with precision because planetary nebulae come in an astonishing variety of shapes. Some are nearly perfect spheres. Others are elliptical. Some have bipolar structures, with two lobes extending in opposite directions. Others look like rings or hourglasses or butterflies or spirals. The shape depends on things like rotation, magnetic fields, the presence of companion stars, and the details of how the material was ejected during the final thermal pulses. The nebula may resemble a glowing ring or cosmic eye. This is one of the more common shapes, a ring-like structure, often with a brighter central star, looking somewhat like an eye staring back at you. It happens when the material is ejected in a thick equatorial disk, but thinner near the poles. When you look at it from certain angles, you see through the thin polar regions to the dense ring, creating the appearance of a circular or elliptical ring with a white dwarf at the center. From Earth, or rather, from wherever Earth used to be, if it still exists, you'd be inside the nebula. You'd be surrounded by it. The view would be surreal. Instead of a single glowing shell far away, you'd see glowing gas in every direction. The sky would be filled with faint, diffuse light, greens and reds and blues, all mixed together. The stars would still be visible through the nebula because it's so diffuse, but they'd be dimmed and perhaps tinted by the intervening gas. And at the center of it all, where the sun used to be, there would be a brilliant point of blue-white light, the exposed core, the white dwarf, shining with the intensity of 100 current suns but compressed into an object the size of Earth. But the real spectacle would be for observers from afar. Observers from afar could see it for millennia. If there are civilizations on planets orbiting other stars, if there are astronomers looking out into the galaxy with their telescopes, they would see a new planetary nebula appear in the sky. It would brighten over a few thousand years as more material is ejected and illuminated. It would reach peak brightness, glowing brilliantly in the darkness. And then, slowly, over tens of thousands of years, it would fade as the gas expands, thins out, and the ultraviolet radiation from the white dwarf weakens. For those distant observers, the death of our sun would be a beautiful, transient event, a reminder that stars, like all things, are temporary. That even something as seemingly eternal as the sun has a beginning and an end, and that in its ending, it creates something beautiful, a luminous monument to billions of years of steady burning, now dispersed into space to seed the next generation of stars and worlds. The planetary nebula phase lasts perhaps 10,000 to 50,000 years. A blink of an eye in cosmic terms, but long enough that multiple generations of intelligent beings, if any still exist in the galaxy at this point, billions of years in the future, could observe it, study it, marvel at it. And at the center of it all, cooling and fading, is what remains of the sun.
The core.
The white dwarf. The final remnant of a star that once burned so brightly, that gave warmth and light to a world teeming with life, that shone for billions of years without fail. The sun's journey is almost over. The nebula will eventually disperse. The gas will merge with the interstellar medium, indistinguishable from the background. And all that will remain is the white dwarf, alone in the darkness, slowly cooling over trillions of years until it becomes a cold, dead ember, a black dwarf, the final fate of all stars like ours. But that takes so long that the universe itself hasn't existed long enough for any white dwarf to become a black dwarf yet. We have time. Not for the sun. Its story is nearly done. But for the universe, for the stars that will form from the sun's ashes, for whatever might come next. The nebula glows. The core cools. And the universe moves on. The white dwarf. The nebula has dispersed. The glowing shells of gas have expanded outward, thinned out, and merged with the interstellar medium. The spectacular light show is over. And what remains, sitting alone in the darkness where the sun used to be, is something small, dense, and utterly unlike the star that came before. The sun's core collapses into a white dwarf. This is the end state, the final form. After billions of years of fusion, expansion, contraction, and mass loss, this is what's left. The white dwarf is not a star in the traditional sense. It's not fusing anything, not generating energy through nuclear reactions. It's a stellar remnant, a corpse, the leftover core of a star that has exhausted all possible fusion pathways available to it. And it's incredibly small. The white dwarf has about half the sun's original mass, compressed down to an object that is roughly the size of Earth. Think about that for a moment. The sun right now has a radius of about 700,000 kilometers. Earth's radius is about 6,400 kilometers. The white dwarf has shrunk by a factor of more than 100 in radius. All that mass, half of what the sun started with, still equivalent to about 160,000 Earths, is squeezed into a sphere roughly the same size as our planet. How is this possible? How can you compress that much mass into such a small volume? The answer lies in the structure of matter at extreme densities. In a normal object, a planet, a human body, even a main sequence star, atoms are mostly empty space. The nucleus is tiny, and the electrons orbit far away from it. There's a lot of room between the nucleus and the electrons. But when you compress matter to extreme densities, the electrons get pushed closer and closer together until they're packed as tightly as quantum mechanics allows. At that point, something called electron degeneracy pressure takes over. This is a quantum mechanical effect. The Pauli exclusion principle states that no two electrons can occupy the same quantum state. When you try to compress electrons into a smaller space, they resist, not because of electromagnetic repulsion but because of this fundamental quantum rule. The electrons push back against compression with a pressure that doesn't depend on temperature. It's a pressure that comes purely from the quantum nature of matter. And that's what's holding the white dwarf up. Not thermal pressure from heat. Not fusion energy pushing outward. Just the quantum mechanical resistance of electrons refusing to be compressed any further. This is called a degenerate state, and it's what allows white dwarfs to exist as stable objects. The result is a density that defies everyday intuition. Density is extreme. A teaspoon weighs tons. 1 cubic centimeter of white dwarf material has a mass of roughly 1 ton. A teaspoon is about 5 cubic centimeters, so a teaspoon of white dwarf matter would weigh about 5 tons. If you could somehow scoop up a teaspoon of this material and bring it back to Earth, ignoring the fact that it would immediately explode due to the change in pressure, it would weigh as much as a large elephant. A sugar cube-sized chunk would weigh about as much as a car. A beach ball-sized sphere would outweigh the entire human population. The density is on the order of 1,000,000 times greater than water, 1,000,000 times greater than rock. It's matter compressed to a state that exists nowhere else in the universe except in the cores of dead stars and, briefly, in the moments before a supernova explosion. And this incredibly dense object is hot. Initial temperature exceeds 100,000 Kelvin. This is the residual heat from billions of years of fusion. The white dwarf isn't generating new heat. There's no fusion happening anymore, but it's still radiating away the heat that's left over from its stellar life. At 100,000 Kelvin, the surface is white-hot, glowing intensely in the ultraviolet. In fact, most of the radiation coming off a young white dwarf is in the ultraviolet, which is why it was able to ionize the planetary nebula in the previous phase. Over time, the white dwarf will cool. It radiates heat into space, and because there's no internal energy source to replace that heat, the temperature gradually drops. It will take billions of years to cool significantly. White dwarfs cool very slowly because they have so much thermal energy stored up and such a small surface area to radiate it away from. What is this object made of? It consists of a carbon-oxygen core. This is the ash of helium fusion, the product of the triple alpha process that dominated the later stages of the sun's life. Carbon and oxygen nuclei, packed together at incredible densities, held up by electron degeneracy pressure. The core is crystalline. At these densities and temperatures, the carbon and oxygen atoms arrange themselves into a regular lattice structure, like a crystal. The white dwarf is, in a very real sense, a giant cosmic diamond. Or, at least, it will be eventually as it cools and the crystallization becomes more complete. But the core isn't the only thing there. Thin helium and hydrogen layers remain on the surface. These are the leftover traces of the original envelope, material that didn't get ejected during the planetary nebula phase. The helium layer might be a few thousand kilometers thick, substantial in terrestrial terms, but incredibly thin compared to the size of the white dwarf itself, less than a tenth of the radius. And on top of that, an even thinner hydrogen layer, perhaps just a few hundred kilometers thick. These layers don't do much. They're not fusing. They're not producing energy. They just sit there, gradually mixing downward into the interior through diffusion over millions of years. They're like the last remnants of the sun's former self, a thin veneer of normal stellar material coating the degenerate core beneath. And that's the key thing to understand. No fusion occurs anymore. The white dwarf is not a star. It's not burning anything. It has no internal energy source. The only energy it has is the heat left over from its past, and that heat is slowly, inexorably radiating away into space. The white dwarf is cooling, fading, dying, not dramatically, not suddenly, but gradually over timescales that dwarf even the main sequence lifetime of the original star. Right now, glowing at 100,000 Kelvin, the white dwarf is incredibly bright despite its small size. It's emitting about as much light as 100 current suns, all from an object the size of Earth. The surface brightness, the luminosity per unit area, is off the charts. If you could somehow stand on the surface of a white dwarf, which you absolutely couldn't because the gravity would crush you into a puddle of subatomic particles, you'd be standing on something hotter and brighter per square meter than anything you've ever experienced. But this brightness is temporary. Without fusion to sustain it, the white dwarf will cool. Over the next few billion years, the temperature will drop from 100,000 Kelvin to 50,000 Kelvin, then to 20,000 Kelvin. The color will shift from blue-white to pure white, then to yellow, then to red. The luminosity will decrease as the temperature drops. Eventually, after tens of billions of years, the white dwarf will cool to the point where it's no longer visible at all. It will become a black dwarf, a cold, dark cinder floating through space. But we're not there yet. The universe is only about 13.8 billion years old, and even the oldest white dwarfs haven't had time to cool completely. Black dwarfs are purely theoretical. They will exist someday, but none exist yet. The oldest white dwarfs in the galaxy are still glowing faintly, still radiating their residual heat, still visible if you have a sensitive enough telescope. From the perspective of what's left of the solar system, the white dwarf is a dramatic change from what came before. During the red giant phase, the sun was enormous, filling half the sky if you were on a surviving planet. Now it's tiny. From Jupiter's orbit, or rather, from where Jupiter's orbit has drifted to due to mass loss, the white dwarf would appear as a bright point of light, perhaps similar in apparent brightness to the sun appears from Earth today, but concentrated into a much smaller disk. It would be a brilliant, blue-white star, small but intensely bright. The outer planets are still there. Jupiter, Saturn, Uranus, Neptune, they all survived the sun's death throes. They drifted outward as the sun lost mass, and now they orbit this tiny white dwarf in a cold, dark solar system. Their moons, frozen solid, orbit in perpetual twilight. The temperature in the outer solar system has dropped dramatically. Without the sun's warmth, the little heat these worlds receive comes only from the fading white dwarf, and it's not enough to make much difference. The outer solar system is colder and darker than it's ever been. And the inner solar system?
Gone.
Mercury consumed. Venus destroyed. Earth, either engulfed or reduced to a lifeless, molten rock, perhaps still orbiting in a wider orbit, baked and barren and alone. Mars, if it still exists, is a frozen, airless ball of rock and ice, all traces of its thin atmosphere stripped away billions of years ago. The solar system that existed for 4.6 billion years, the system that gave birth to life on Earth, the system that was home to countless worlds and moons and asteroids and comets, it's been reduced to this. a handful of outer planets orbiting a cooling ember, a graveyard, a tomb. But even in death, the sun has a legacy. The carbon and oxygen locked in the white dwarf, the elements dispersed in the planetary nebula, the enriched gas that will someday become part of new stars and planets. That's the sun's contribution to the universe. The atoms that made up the sun, that were forged in its core through billions of years of fusion, will live on. They'll be incorporated into new worlds, new stars, perhaps even new forms of life billions of years in the future. The white dwarf itself will persist for an unimaginably long time. It will cool slowly, fading from white to yellow to red to black, taking trillions of years to reach thermal equilibrium with the cosmic microwave background. Long after galaxies have merged, long after the last stars have formed, long after the universe has expanded and cooled to the point where nothing new can happen, the white dwarf that was once our sun will still be there, cold, dark, invisible, but real. A monument to a star that once gave life. A testament to the impermanence of all things. A reminder that even the sun, as eternal as it seems, is just a temporary configuration of matter and energy, destined to evolve, change, and ultimately fade away into the darkness. This is what the sun becomes. Not a supernova, not a black hole. Just this, a small, dense, cooling sphere of degenerate matter, orbited by a few frozen worlds, drifting through the galaxy in silence. The end of the story. The final chapter. The sun's journey is complete. The long, dark future. And now we enter a timescale that's almost impossible to comprehend. We've already talked about billions of years, the time it took for the sun to age, to swell into a red giant, to shed its layers and become a white dwarf. But now we're talking about something far longer. Something that dwarfs even those immense spans of time. The white dwarf cools over trillions of years. Trillions. Not billions. Trillions. To put this in perspective, the universe right now is about 13.8 billion years old. The sun's total lifespan from birth to white dwarf is about 10 billion years. But the cooling time for a white dwarf? That's measured in trillions of years. 10 trillion years. 20 trillion years. Maybe more, depending on how you define fully cooled. This is a timescale so long that it's difficult to find anything meaningful to compare it to. All of recorded human history is about 6,000 years. The entire evolution of complex life on Earth, from the first multicellular organisms to now, is about 600 million years. The age of the universe, the time since the Big Bang, is 13.8 billion years. And we're talking about the white dwarf cooling for 10 or 20 trillion years. That's 1,000 times longer than the current age of the universe. Why does it take so long? Because the white dwarf has no internal energy source. It's not fusing anything. It's not generating heat. All it can do is radiate away the thermal energy it already has. And it has a lot of thermal energy stored up. Billions of years of fusion have left the interior incredibly hot, even if the core itself is no longer undergoing nuclear reactions. That heat has to work its way from the interior to the surface and then radiate away into space. And because the white dwarf is so dense, heat moves through it very slowly. It's an excellent insulator in a sense. The cooling process is incredibly gradual. At first, the cooling is relatively fast. The surface temperature drops from 100,000 Kelvin to 50,000 Kelvin over the first few hundred million years. Then from 50,000 to 20,000 over the next few billion years. The white dwarf shifts from blue-white to yellow. But as the temperature drops, the cooling rate slows down. Going from 20,000 Kelvin to 10,000 Kelvin takes longer than going from 100,000 to 50,000. Going from 10,000 to 5,000 takes even longer. The curve flattens out, and so it slowly fades. The luminosity decreases as the temperature drops. A white dwarf at 100,000 Kelvin might be as bright as 100 current suns. At 50,000 Kelvin, it's more like 10 suns. At 10,000 Kelvin, it's a fraction of the current sun's brightness. At 5,000 Kelvin, roughly the temperature of the sun's surface today, it's putting out only a tiny fraction of the light the sun produces now because it's so much smaller. The white dwarf continues to cool. 5,000 Kelvin, 4,000, 3,000. It glows dull red now, barely visible. The luminosity has dropped to 1/10,000th of the current sun's output, maybe less. And it keeps cooling. 2,000 Kelvin, 1,000, 500. Eventually, it becomes a black dwarf. This is the theoretical end state of a white dwarf, an object that is cooled to the point where it no longer emits any visible light. It's reached thermal equilibrium with the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. At that point, it's effectively invisible, a cold, dark sphere of degenerate matter, floating through space, undetectable except by its gravitational influence. But here's the thing, no black dwarfs exist yet. The universe is too young. Even the oldest white dwarfs in the universe, the ones that formed from the very first generation of stars billions of years ago, are still cooling. They're faint, yes. They're cold compared to young white dwarfs. But they're still glowing, still radiating, still detectable. The universe simply hasn't existed long enough for any white dwarf to cool all the way to a black dwarf. Current estimates suggest it takes somewhere between 10 and 20 trillion years for a white dwarf to become a black dwarf, depending on its mass and composition. The universe is 13.8 billion years old. That means we'd need to wait about another 10 trillion years, about 700 times longer than the universe has currently existed, before the first black dwarfs appear. By the time the sun becomes a black dwarf, the universe will be unrecognizable. Star formation will have ceased. All the gas in galaxies will have been used up or ejected. The last stars will have burned out. The universe will be dominated by stellar remnants, white dwarfs, neutron stars, black holes, and planets, all drifting through an ever-expanding void that's darker and colder than we can imagine. But let's bring this back to something more tangible. What happens to the sun, the white dwarf, the black dwarf-to-be, over these immense timescales? The sun becomes invisible to the naked eye. Long before it becomes a true black dwarf, it will have faded to the point where you couldn't see it anymore without a telescope, even if you were relatively close to it. After a few trillion years, the white dwarf might have a surface temperature of just a few hundred Kelvin, far too cool to emit visible light. It would glow faintly in the infrared, but to the human eye, it would appear as nothing more than a dark sphere, perhaps slightly warmer than the surrounding space, but effectively invisible. If you were standing on one of the surviving planets, say Jupiter or Saturn, though standing on a gas giant is impossible, you wouldn't see a sun in the sky anymore. There would be no daylight, no warmth, just the faint light of distant stars, and perhaps the glow of the Milky Way stretching across the sky. The solar system would be a dark, frozen place, indistinguishable from the depths of interstellar space. And speaking of those surviving planets freeze permanently. Whatever warmth they once received from the sun, however little that was, especially for the outer planets, is gone now. Jupiter, with its internal heat from gravitational contraction, might generate a tiny bit of warmth for a while longer, but even that will eventually fade. The moons of the outer planets, which might have briefly experienced liquid water or temperate conditions during the red giant phase, are now frozen solid, their surfaces coated in ice that will never melt again. Any atmosphere these moons might have had will freeze out and fall to the surface as frost. The temperature will drop to just a few degrees above absolute zero, limited only by the faint warmth of the cosmic microwave background. These worlds become frozen time capsules, preserving whatever geological features or chemical compositions they had at the end of the sun's active life, unchanging for trillions of years. But even this frozen configuration isn't stable forever. Over immense timescales, the solar system is subject to gravitational perturbations from outside. Galactic encounters may eject planets entirely. The Milky Way is not a static place. Stars pass by each other. The galaxy itself is in motion, orbiting, rotating, interacting with other galaxies. And occasionally, very occasionally, a star will pass close enough to the solar system to gravitationally perturb the orbits of the planets. When a star passes within a light year or so of the solar system, its gravitational pull can tug on the planets, changing their orbits. If the encounter is close enough, A planet can be flung out of the solar system entirely, ejected into interstellar space. The outer planets are especially vulnerable to this because they're less tightly bound to the white dwarf than the inner planets would have been. Over trillions of years, these encounters add up. Models suggest that most planetary systems will eventually be disrupted by close stellar encounters. One by one, the planets are ejected. Jupiter goes first, perhaps flung out by a passing star a few trillion years from now. Then Saturn. Then Uranus and Neptune. Each one leaves the solar system and becomes a rogue planet, drifting through interstellar space alone, no longer bound to any star. Or perhaps one of the planets collides with a white dwarf, spiraling inward over billions of years due to gravitational radiation, tiny ripples in space-time that carry away orbital energy. Or maybe the planets survive, remaining in orbit around the white dwarf for tens of trillions of years, until another galaxy merges with the Milky Way and the gravitational chaos disrupts everything. But through it all, the remnant continues orbiting the Milky Way. The white dwarf, whether it still has planets or not, remains part of the galaxy. It orbits the galactic center just as the Sun did, making one orbit every 200 to 250 million years. It passes through spiral arms, through regions of space that were once dense with stars and gas, but are now mostly empty. It drifts through the galaxy, an invisible remnant of a star that died long ago. And the galaxy itself is changing. The Milky Way will merge with the Andromeda Galaxy in about 4.5 billion years, long before the Sun even becomes a red giant. The merged galaxy, sometimes called Milkomeda, will be larger and more elliptical than either of the original galaxies. The Sun, whether it's still a main sequence star or has already become a white dwarf at that point, will be swept up in this merger, its orbit drastically altered by the gravitational chaos of billions of stars interacting. After the merger, the Sun, or its white dwarf remnant, will orbit the center of this new, larger galaxy. And over tens of billions of years, as star formation in the galaxy gradually ceases and the gas is used up, the galaxy will become a collection of aging and dead stars. Red dwarfs, the smallest and longest-lived stars, will continue burning for trillions of years. But eventually, even they will die. The galaxy will become a graveyard of white dwarfs, neutron stars, and black holes, all orbiting a supermassive black hole at the galactic center. And the Sun will be one of countless white dwarfs in this dead galaxy, indistinguishable from all the others, slowly cooling in the darkness. This is the long dark future. Not dramatic, not violent, just slow, cold, and empty. The universe expands. The cosmic microwave background cools. The temperature of space drops closer and closer to absolute zero. Stars burn out one by one. Galaxies drift apart from each other as the expansion of the universe accelerates, pushed by dark energy. Eventually, galaxies become isolated, unable to see each other, each one alone in an ever-expanding void. And in one of those galaxies, in a region of space that was once a vibrant solar system with planets and moons and perhaps even life, there is a small, dark, invisible sphere of degenerate matter. The black dwarf that was once our Sun cold. Silent, unchanged and unchanging, drifting through space for all eternity. Or perhaps not quite eternity. Some theories suggest that even black dwarfs are not the final state. Over timescales of 10^1500 years or more, a number so large it's almost meaningless, quantum tunneling could cause the carbon and oxygen nuclei in the black dwarf to fuse into iron, the most stable element. The black dwarf would slowly, atom by atom, convert itself into a sphere of solid iron. And then, even further in the future, the iron itself might decay through proton decay, if protons are indeed unstable on extremely long timescales. The black dwarf would evaporate, particle by particle, until nothing remains. But these timescales are so vast that the universe, as we know it, would be utterly unrecognizable long before they're reached. For all practical purposes, the black dwarf is the end. The final state. The ultimate fate of a star like the Sun. From a brilliant, life-giving ball of fusing hydrogen, to a bloated red giant, to a tiny white dwarf, to a cold black dwarf, invisible and alone. That's the journey. That's the story of the sun, from beginning to end. And the question we started with, what will we see when the sun dies, has an answer. We'll see beauty. We'll see terror. We'll see transformation on a scale that's hard to comprehend. We'll see the inner solar system destroyed, the outer solar system frozen, and a glowing nebula marking the spot where our star used to be. And then, eventually, we'll see nothing at all. Just darkness. Just the cold, empty silence of a universe that has moved on. That's what we'll see. That's what awaits. Not in our lifetimes, not for billions of years, but inevitably. The sun will die. And when it does, everything we know will die with it. Cosmic context. Let's step back for a moment. We've been focused so intently on the sun, our sun, the star that defines our existence, that it's easy to forget this story isn't unique. What happens to the sun isn't special. It's not a rare cosmic event or an anomaly. It's ordinary,
Common.
unremarkable in the grand scheme of things. The sun's nebula joins millions of others. When the sun sheds its outer layers and creates that beautiful, glowing planetary nebula, it becomes one of countless such objects scattered throughout the galaxy. Right now, in the Milky Way alone, there are thousands of planetary nebulae that we can observe. And those are just the ones that are currently glowing, currently visible. Over the history of the galaxy, there have been millions, perhaps hundreds of millions, of planetary nebulae. Every single one represents a star that died. A star that went through the same process the sun will go through. It fused hydrogen for billions of years. It swelled into a red giant. It shed its outer layers. It left behind a white dwarf. And for a brief period, tens of thousands of years, it created a luminous cloud that could be seen across the galaxy. And such nebulae are common in galaxies. Not just in the Milky Way, but everywhere. When we point our telescopes at other galaxies, we see planetary nebulae there too. In the Andromeda Galaxy, in the Triangulum Galaxy, in distant galaxies billions of light-years away, planetary nebulae are a universal phenomenon. They're part of the standard life cycle of stars across the entire universe. Why are they so common? Because the vast majority of stars end this way. About 90% of stars die this way. That's not a rough estimate. It's a well-established fact. The universe is full of low and intermediate mass stars, stars between about 0.5 and 8 solar masses. These are the stars that become red giants and then planetary nebulae. They're the most common type of star. And when they die, they all follow the same basic script. The massive stars, the ones more than 8 solar masses, they're the exception. They're rare. They live fast, burn bright, and explode as supernovae. They're spectacular, yes. They're dramatic. They produce neutron stars and black holes. They're the rock stars of the stellar world. But they're outnumbered 10 to 1 by the smaller, quieter stars that die as planetary nebulae. The sun is part of that majority. It's a middle-of-the-road star, average in almost every way. Its mass, its temperature, its luminosity, its lifespan, all of it is typical for a star of its type. And its death will be typical too. Why doesn't the sun explode as a supernova? Why can't it create a black hole? Because the sun obeys the Chandrasekhar limit. This is a fundamental threshold in astrophysics, discovered by the Indian physicist Subrahmanyan Chandrasekhar in the 1930s. The Chandrasekhar limit defines the maximum mass a white dwarf can have before it collapses further. The limit is about 1.4 solar masses. If a white dwarf exceeds this mass, electron degeneracy pressure, the quantum mechanical force that holds white dwarfs up, can no longer support the star against gravity. The white dwarf collapses. If it's in a binary system and accreting matter from a companion, this collapse might trigger a Type Ia supernova. If it's isolated, it might collapse all the way down to a neutron star, though that's less common. But the key point is this. The sun's white dwarf will have a mass of only about 0.5 to 0.6 solar masses. That's well below the Chandrasekhar limit. It's not even close. The sun lost too much mass during the red giant and AGB phases. It shed 40 or 50% of its original mass into space. What's left isn't massive enough to overcome electron degeneracy pressure. The white dwarf is stable. It will never collapse further. And because the sun isn't massive enough to create a white dwarf above the Chandrasekhar limit, it never becomes a supernova. There's no explosion, no neutron star, no black hole, just a white dwarf that slowly cools over trillions of years. That's the fate of all stars like the sun. It's set in stone by the laws of physics, determined by mass and nothing else. But even though the sun's death isn't explosive, it's still important. It still contributes to the galaxy in a meaningful way. Its death helps seed future star systems. Think about what happens when the sun creates its planetary nebula. All that material, carbon, oxygen, nitrogen, helium, traces of heavier elements, is ejected into the interstellar medium. It spreads out, mixes with gas and dust that's already floating between the stars, and becomes part of the raw material from which new stars will form. Star formation is a cycle. Stars form from collapsing clouds of gas and dust. They live for millions or billions of years, fusing lighter elements into heavier ones. They die, ejecting some or all of their material back into space. That material enriches the interstellar medium, and the next generation of stars that forms from it has a higher proportion of heavy elements. Those stars live and die, enriching the medium even further.
And so on.
The first stars in the universe were made of almost pure hydrogen and helium, the only elements created in the Big Bang. But every subsequent generation has been richer in heavy elements because of the deaths of previous generations. The sun itself is a third-generation star, maybe fourth generation. It formed from gas that had already been enriched by earlier stars. That's why the sun contains carbon, oxygen, iron, silicon, and all the other heavy elements. Those elements were created in stars that died before the sun was born. And now the sun will contribute to the next generation. Elements forged inside the sun become part of new worlds. The carbon and oxygen created through helium fusion, the nitrogen produced through CNO cycle reactions, the traces of neon, magnesium, sulfur, and other elements. All of it will be dispersed into space. Some of it will remain as isolated atoms in the interstellar medium, but some of it will eventually become part of a new collapsing cloud, a new protostar, a new planetary system. Perhaps, billions of years from now, a new star will form from a cloud that contains atoms that were once part of the sun. Perhaps planets will form around that star, rocky planets made of silicates and metals that include carbon and oxygen from the sun's core. Perhaps life will arise on one of those planets, building its biochemistry from carbon atoms that spent billions of years inside the sun, fusing and transmuting in the stellar furnace. In a very real sense, the sun will live on, not as a star, not as a conscious entity, but as a collection of atoms scattered throughout the galaxy, incorporated into new structures, new worlds, new possibilities. This is the cosmic cycle of matter. Nothing is ever truly destroyed. Everything is recycled. The atoms in your body have been part of countless stars, countless planets, countless organisms. They've existed for 13.8 billion years, since the Big Bang, and they'll continue to exist for trillions of years more, long after you're gone, long after Earth is gone, long after the sun is gone. You are quite literally made of stardust. And when you die, you'll return to stardust. And so will the sun. But what about the solar system itself? What about the structure, the organization, the arrangement of planets and moons and asteroids that has existed for 4.6 billion years? The solar system becomes cosmic debris. Over time, the configuration falls apart. We've already talked about how planets might be ejected by close stellar encounters, or how they might spiral into the white dwarf, or how they might simply drift farther and farther out as the sun loses mass. But eventually, one way or another, the solar system as a coherent structure ceases to exist. Maybe Jupiter ends up as a rogue planet, wandering through interstellar space, no longer orbiting any star. Maybe Neptune gets captured by another star during the Milky Way-Andromeda merger, becoming part of a different planetary system. Maybe one of the inner rocky remnants, whatever's left of Earth or Venus, falls into the white dwarf, its atoms torn apart by tidal forces and mixed into the outer layers of the degenerate star. Whatever the specific fate of each planet, the end result is the same. The solar system disperses. The planets go their separate ways. The organized structure that existed for billions of years breaks down into chaos. And what remains are individual objects, each following its own path through the galaxy, no longer connected to each other or to the star that gave them birth. This is the fate of all planetary systems. Eventually, nothing lasts forever. Not stars, not planets, not galaxies, not even the universe itself if current models of its expansion are correct. Everything is temporary. Everything is transient. We live in a universe where structure arises from chaos, persists for a while, and then dissolves back into chaos. Stars are born, they live, they die. Planets form, they orbit, they're ejected or destroyed. Galaxies merge, evolve, and eventually fade. It's the fundamental nature of reality. But in that impermanence, there's a strange kind of beauty. The fact that the sun will die makes it more precious, not less. The fact that Earth's time is limited makes life more remarkable, not less. We exist in a brief window of cosmic history, in a brief period of stellar stability, on a planet that happened to form at just the right distance from just the right star to allow liquid water and complex chemistry and evolution and consciousness. That's not fate. That's not destiny. That's just luck. Billions upon billions of stars in the galaxy, and we happen to be orbiting one that's stable enough, long-lived enough, and positioned in a quiet enough region of the galaxy to allow life to flourish for billions of years. We won the cosmic lottery. And the sun's eventual death doesn't diminish that, it emphasizes it. The sun is one star among hundreds of billions in the galaxy, and billions of trillions in the observable universe. Its death will be one planetary nebula among millions, one white dwarf among countless others. In the grand cosmic context, the sun is insignificant. But to us? To the life that arose on Earth? To the civilizations that might one day spread through the solar system and beyond? The sun is everything. It's the source of all the energy that powers life on Earth. It's the reason our planet is warm enough for liquid water. It's the center of our world, literally and figuratively. And when it dies, that world ends. Not because the universe cares, but simply because that's what happens when stars age. It's physics. It's chemistry. It's the inevitable progression of matter and energy toward equilibrium. The sun will die. The solar system will disperse. The atoms will be recycled. And the universe will continue, indifferent and unchanging in its fundamental laws, even as everything within it changes constantly. That's the big picture. That's the cosmic context. The sun's death is both momentous and insignificant, both unique and utterly common. It's the end of our world, and just another Tuesday in the life of the galaxy. And maybe that's the most profound realization of all. Closing thought. So we return to the question we started with. What will we see when the sun dies? We'll see fire. We'll see ice. We'll see the slow transformation of something stable and life-giving into something chaotic and destructive. We'll see planets consumed, worlds frozen, and the familiar order of the solar system torn apart and scattered. We'll see a nebula glowing in the darkness, beautiful and terrible, marking the spot where our star used to be. And eventually, we'll see nothing at all, just a small, fading ember where the sun once burned. But perhaps the more important question is this. Will anyone be there to see it? The sun gives life, and eventually takes it away. This is the fundamental paradox at the heart of our existence. The sun is the reason life exists on Earth. Every photon of sunlight that hits our planet carries energy that was generated in the sun's core through nuclear fusion. That energy drives photosynthesis in plants. Plants produce oxygen and organic compounds. Animals eat plants or eat other animals that eat plants. The entire food chain, the entire biosphere, ultimately traces back to the sun's energy. Without the sun, Earth would be a frozen, lifeless rock drifting through space. The temperature would be just a few degrees above absolute zero. The oceans would be solid ice hundreds of kilometers deep. The atmosphere would freeze and fall to the surface as frost. There would be no weather, no seasons, no day or night, just eternal darkness and cold. Life as we know it couldn't exist. The sun made us possible. But that same sun will also destroy us. Not out of malice, not out of intention, but simply by following the laws of physics. Stars age. They evolve.
They change.
And when they do, anything that depends on their stability is doomed. The sun will warm Earth too much, then cook it, then possibly swallow it whole. The life giver becomes the life taker. The source of all energy becomes the source of destruction. And here's the truly sobering part. Earth's fate is sealed long before the final act. We've talked about the red giant phase, about the sun swelling up and engulfing the inner planets 5 billion years from now. That's the dramatic finale. That's the spectacle everyone imagines when they think about the sun's death. But Earth dies long before that. In a billion years, maybe 1.5 billion at most, the oceans boil away. The atmosphere becomes unbreathable. The surface temperature exceeds anything that could support complex life. Earth becomes uninhabitable while the sun is still technically a main sequence star, still fusing hydrogen in its core, still billions of years away from its red giant phase. Life on Earth doesn't end with a bang. It ends with a slow burn. The sun gets gradually brighter, the temperature rises, the climate becomes increasingly unstable, and eventually, the conditions that allowed life to flourish for billions of years simply disappear. The biosphere collapses. The last organisms die out. Earth becomes a sterile, dead world while the sun is still shining steadily, oblivious to the extinction it's causing. And that means if humanity, or whatever species evolves from humanity, or whatever form of intelligence exists on Earth billions of years from now, wants to survive, there's only one option. Humanity's survival depends on leaving its birthplace. We have to leave Earth. Not eventually. Not someday. If we want our descendants to witness the sun's death from a safe distance, if we want any part of human civilization to persist beyond the next billion years, we have to become a spacefaring species. We have to build habitats in space, terraform other worlds, travel to other star systems. We have to sever the connection between humanity and Earth, between our survival and the survival of our home planet. This is an almost impossible thing to contemplate. Earth is all we've ever known. It's where we evolved, where our entire history has unfolded, where everything we've ever built or created or loved exists. The idea of leaving it behind, permanently, is both terrifying and heartbreaking. But the alternative is extinction. If we stay on Earth, we die with Earth. That's not pessimism. That's just physics. Maybe we'll make it. Maybe, 1 billion years from now, humans or our descendants or intelligences we've created will have spread throughout the galaxy. Maybe we'll have colonies on thousands of worlds, artificial habitats orbiting countless stars, technologies we can't even imagine today. Maybe the death of the sun will be a distant, almost nostalgic event, witnessed by beings who remember Earth the way we might remember the African savanna where our species first evolved, important historically, but no longer central to our existence. Or maybe we won't make it. Maybe we'll destroy ourselves long before the sun becomes a threat. War, disease, environmental collapse, our own short-sightedness and tribalism. There are so many ways human civilization could end before we ever get the chance to become a truly spacefaring species. Maybe in 1 billion years, there will be no humans left to witness the oceans boiling away. Maybe Earth will die alone, its biosphere extinguished, its landscapes erased, with no one left to remember that life ever existed here at all. We don't know. We can't know. The future is unwritten. But what we do know is that the clock is ticking. Not urgently. We have time, plenty of time, at least by human standards. But the countdown has begun. Earth has an expiration date. And if we want to survive beyond that date, we need to plan for it. We need to work toward it. We need to take the first steps on a journey that will span thousands of generations and billions of years. And when the sun finally does die, when it sheds its outer layers and creates that glowing planetary nebula, what'll be left? When the sun dies, it leaves behind a silent, glowing ghost. A shell of gas expanding into space, illuminated by the ultraviolet radiation from the white dwarf at its center. A monument to 10 billion years of stellar evolution. A marker indicating that a star once burned here, giving warmth and light to a system of planets, at least one of which harbored life. The nebula will glow for tens of thousands of years. Brilliant greens and reds and blues, visible from across the galaxy to anyone with a telescope powerful enough to see it. And then it will fade. The gas will disperse. The white dwarf will cool. And eventually, there will be nothing left but a dark, invisible sphere of degenerate matter, drifting through space in silence. No light, no heat, no life, just the cold, empty remnant of what used to be. But if we've done our job, if humanity or its descendants have survived, if we've carried the torch of consciousness and intelligence forward into the far future, then the sun's death won't be the end of our story. It will just be one chapter. A significant chapter, certainly. The death of our home star, the end of the solar system that gave us birth. But not the end of us. We'll remember the sun. We'll tell stories about it. We'll point to the fading nebula in the sky and say, that's where we came from. That star, that planet, that brief moment in cosmic history when conditions were just right for life to arise and intelligence to emerge. That's our origin. That's our legacy. And maybe, just maybe, we'll take the elements that the sun scattered into space, the carbon, the oxygen, the nitrogen, all the building blocks of life, and we'll use them to seed new worlds, to create new biospheres, to give life another chance in corners of the galaxy where it might never have arisen on its own. The sun created us. It nurtured us. It sustained us for billions of years. And in its death, it will give us one final gift, the raw materials for new creation, new possibilities, new beginnings. That's what we'll see when the sun dies. Not just an ending, but a transformation. Not just death, but rebirth.
The sun will die, yes.
But in dying, it will become part of something larger, part of the ongoing cycle of matter and energy that has been running since the Big Bang and will continue for trillions of years to come. We are stardust. The sun is stardust. Everything is stardust. And when the sun returns to dust, scattering itself across the galaxy in a glowing cloud of atoms, it will be joining countless other stars that have made the same journey, contributing to the same cosmic cycle that makes everything, stars, planets, life itself, possible. So, what will we see when the sun dies? We'll see the end of an era, the closing of a chapter, the death of the star that made us possible. But if we're wise, if we're brave, if we're lucky enough to survive that long, we'll also see hope. Because the universe doesn't end when one star dies. It goes on. And so can we if we choose to. We can carry the light forward, even when the sun goes dark. We can become the inheritors of billions of years of stellar evolution, the caretakers of consciousness in a universe that seems utterly indifferent to its existence. The sun will die. That's certain. But what we do with the time we have before that happens, that's up to us. And maybe that's the most important lesson we can take from the sun's inevitable death. Nothing lasts forever. Not stars, not planets, not civilizations. But that doesn't mean what we do doesn't matter. It means exactly the opposite. It means we have to make the most of the time we have, to cherish the improbable gift of existence, to look up at the sun each day and remember that it won't always be there, and neither will we. So look up. Look at the sun, carefully, not directly, but look at it. Feel its warmth on your skin. Remember that the light touching you right now left the sun's surface 8 minutes ago, carrying energy that was generated in the core over the course of millions of years as photons slowly random walked their way from the center to the surface. Remember that this light has been shining on Earth for 4.5 billion years and will continue to shine for billions more. Remember that we are impossibly lucky to exist in this brief window of cosmic time when conditions are just right for life, for consciousness, for beings capable of looking up at the stars and understanding, really understanding, what they are and how they work. The sun will die. But right now, in this moment, it's alive. It's burning. It's pouring energy into the solar system, making everything possible. And we're here to witness it. That's the miracle. That's the gift. That's what we'll remember when the sun is gone. And if we survive long enough to see that day, to watch the planetary nebula fade into darkness, to witness the final transformation of the star that gave us life, we'll look back on these early days, our time, right now, and we'll remember what it was like to live under a stable, yellow sun. We'll remember Earth. We'll remember home. And we'll carry that memory forward into whatever future awaits us.
The sun will die.
But the story doesn't have to end there. Not if we don't let it.